In this example, we're going to look at the magnetic field of a coax. So we're going to revisit our old friend, the coax geometry, but we're going to look specifically at the magnetic field properties associated with it. So remember, a coax has a center conductor of radius A, and then there's an outer conductor, and we'll call this outer radius B. And in between is a dielectric. We're going to, in this case, we're just going to call it a vacuum. So it's just going to be mu naught in here. And for the purposes of orientation, we're going to say that it's going along the z-axis. So, and then over here you have a current I that's going along the center conductor. So current I. Now to fully characterize this, let's talk about, and since the current is, so this current I, we're going to say it's in the positive z direction, and then since this is a closed circuit, in the outer conductor, you're going to have a current of negative IZ. So the current's going to come out of the screen in the positive z direction, and then in the outer conductor, it's going to go into the screen in the minus z direction. So we're going to calculate two things. We want to find the inductance per unit length, which is something that which is a key parameter that we use in our transmission line discussion. So we should arrive at a formula that looks somewhat similar. And then separately, we also want to know what the energy stored, magnetic energy stored per unit length is. So to start, to find the inductance per unit length, let's start by finding the magnetic field itself to go from there. So in this case, we can use Ampere's circuit law, where HdL across a circle clothesline integral, which will look like this, of radius rho. That clothesline integral is going to give you what? It's going to be equal to the current going through it. And in this case, because of symmetry, you'll see that we can pull the H out and everything works out, right? So we can pull the H out and then come up with a closed form solution for the magnetic field. So let's, just to more rigorously figure out what the current is, let's think about the current in terms of the current density in this z direction integrated across the surface. So let's start with the left-hand side of the equation. So H dl, given the right-hand rule, we know we have a bunch of current coming in the positive z direction. If you point your thumb out of the screen here and curl your fingers around, you can see that the magnetic field you expect to be in the phi direction. So H is going to be equal to some quantity H phi in the phi direction. And from symmetry, you can see that it doesn't depend on phi. So you will be able to, it doesn't depend on phi and it doesn't depend on z if this was infinitely long, right? Because if you rotate this way, if you go up, the situation looks the same. So let's write that out. 0. So in this case, your clothesline integral looks like this. So you're going to integrate as a function. You're going to have h phi in the phi direction dot, and you're going to integrate along this line, right? This is the d phi direction. So I just write d phi phi hat, right? Note what's missing. This is not a unit length. So whenever you write d phi, you always have to multiply by rho. Right, so this is our dl, this is our h dot dl. The phi dot phi is going to be equal to 1. So then you're left with rho is a constant when we're talking about phi, right? So for the purposes of d phi, your h and your rho are both constants. So you pull that out, integral 0 to 2 pi of d phi, and you end up with 2 pi h phi rho. Now let's look at the right-hand side of the equation. What's j dot ds if this is our surface? So j dot ds, it's going to depend on what your radius is, right? So if your radius is inside the conductor, you're going to have what? In the case of these coaxes, I guess one thing to keep in mind is that the current, in this case, we're going to look at this in terms of two hollow cylinders. So inside, if all the current is going along this outer edge, the current's going to be 0 in here. So it's going to be 0 for rho less than A. And then as soon as you increase the radius such that this inner conductor, this inner cylinder is encapsulated, then the total current going through is going to be equal to the current across this whole thing, right? It's going to be I if rho is between A and B. But then once your rho expands so that it's out here, then this positive I in the plus z direction gets canceled out by this I that's in the minus z direction. So then the total current going through the surface is now going to be 0. So for rho greater than B, it's going to be 0 again. So you have this piecewise defined value of the left-hand side of the equation. And so if you combine these two together, in this case, let's start by finding what we really want is the magnetic flux density, which is going to be equal to mu h. And mu h is going to be, h is going to be in terms of h phi, right? So we can divide this 2 pi rho over. It's going to be j dot ds of 2 pi rho in the phi direction, where this j dot ds is dependent on what rho is over here, right? So b is going to be equal to 0 for rho less than A. And then if you're in between A and B, it's going to be equal to what? It's going to be equal to mu I over 2 pi rho in the phi direction. And then if rho is greater than B, it's going to be 0 again. So now we have this expression for the magnetic flux density, and we can start calculating the inductance. So to find the inductance per unit length, we're going to have to change our perspective a little bit. But what we want, the flux lines are going around in this direction, right? So to capture the total amount of flux that's generated, we want a ds that looks like this, right? Where we're capturing the flux lines that go around the center coax like that. So we're going to capture all that. That's going to be the total amount of flux that's created by this current that's running through the coax. So recall, to find the inductance per unit length, we would want to evaluate over this surface, which is in the dimension of rho, right? This is rho as well as z. So our ds in our future surface integral is going to be d rho dz. And the surface vector, the normal vector that describes the surface, is going to be in the phi direction. So circling back, our inductance per unit length, remember, inductance is the total amount of flux that's created over a certain area. So in this case, that's going to be the flux density, which we calculated, the magnetic flux density, divided by the current it took to get there, where ds is this over here, and b is defined as over there. So let's plug in our values. We have 1 over I. We're integrating, let's say, per unit length. So we're going to integrate z from 0 to 1 so that it's per unit length, since we want the inductance per unit length. In terms of rho, we're going to integrate between A and B, since that's the portion that's non-zero. And then we find our b dot ds, right? Our b in this case is mu I over 2 pi rho phi, and our ds is d rho dz in the phi direction. So that gives us the i's cancel, so that part's nice, which is good because the inductance should not be dependent on the amount of current that you have going in there. And you're going to have z goes from 0 to 1, rho goes from A to B of mu over 2 pi 1 over rho d rho dz. Separate this out even more. Let's pull out our constants. So we have mu over 2 pi and then we don't have any z's, so dz 0 to 1. In our rho, rho goes from a to b of 1 over rho d rho. So the integral of 1 over rho is the natural log of rho. So we have, recall that if you have natural log of b minus natural log of a, you can combine them, in the case of natural logs, to be natural log of b over a. So plugging that in, we have that the inductance per unit length is going to be equal to mu over 2 pi natural log of b over a. And this should be an expression that you can find in the text in the transmission line portion of our discussion for coaxial lines. And then separately, so we're mostly there, we also wanted to find the total amount of energy stored, right, for a unit length. And so to do that, remember our basic amount, our total amount of energy stored would be the volume integral of 1/2 mu and then h squared, right, dv. So in this case, h would be this divided by mu, so we just have I over 2 pi rho. So we would simply have, so now the hard part is just doing the integral. So WH is going to be equal to, we're going to go z equals 0 to 1 for unit length. Phi is going to go from 0 to 2 pi, and our rho is going to go from a to b, because that's the part that's non-zero. And we're going to have 1/2 mu, and then our h field, we said, is 1 over 2 pi rho, right? So 1 over 2 pi rho, and we're going to square it. So we're going to have I squared over 4 pi squared, 1 over rho squared, and then our dv is going to be rho, d rho, d phi, dz, right? D rho, dz, and then d phi has to have a rho in it. So now we just have to write out that integral. So let's pull out everything that is a constant for the purposes of this calculation. So we have, so this 2 times 4 gives us the 8. So you have 8 pi squared on the bottom. We have mu I squared on the top. We have no z's, so it's just dz going from 0 to 1. That's going to give us 1. D phi goes from 0 to 2 pi, and there's no phi in here, so that's just going to give you 2 pi. And then we have 1 over rho squared, right? So, oh wait, actually, so this rho cancels out with that rho, so we just have 1 over rho d rho going from a to b. So given our previous calculation here, we know this is going to be the natural log of b over a. And so that gives us our final solution, that the amount of energy stored is going to be mu I squared over 4 pi. Thanks to the help of this 2 pi and this 8 pi squared gives us 4 pi, natural log of b over a. One thing to note is that if you look at this, you have you can also rewrite this. I'll just squeeze that in here. But if you plug in that L is equal to mu over 2 pi natural log over a, you can rewrite this as 1/2 of. So if you pull out a 1/2 here, you're left with 1/2 mu I squared over 2 pi natural log of b over a. Let's just pull out that I squared out here. And what is this quantity here? This is actually L. So one nice thing that might help give you some confidence that this is the correct answer is you actually do have the circuit theory conclusion that the total energy stored per unit length is indeed 1/2 Li squared. And so there you have it. This is a nice example because it covers, it ties back to a transmission line result and also goes through the process of calculating the magnetic fields using Ampere's circuits law, relating that to inductance, and also calculating the total energy stored. Now, as a quick postscript, I think it's also worth pointing out there are other examples where this is not a hollow cylinder, And so your solution for the magnetic field for rho less than A is going to be a little bit different if this is not a hollow cylinder. But we can still tie it to the coaxial equations, regardless of whether this is treated as a hollow cylinder or not. Because if we talk about it in terms of just the total current, all of the math related to deriving the coax equations are in the region between A and B, where the fact of whether it's a hollow cylinder or a completely solid center core is all result in the same equation for this region. And so the result matches the coaxial transmission line, but it's also worth clarifying that in previous coax examples, there are situations where this is also this is not a hollow cylinder, in which case this would not just be zero, it would just be something that gradually increases as rho increases, and you can refer to that example for the exact equation. But everything beginning from rho greater than A throughout will be the same, regardless of whether this is hollow or not.